In this video lecture, we will discuss three different points. Limitation of open chain structure of glucose. Second, evidences in favor of ring structure of glucose. And third one, establish ring structure of glucose. Let us consider all 3 points one by one. Limitation of open chain structure of glucose. On the basis of certain reactions, it has been confirmed that open chain structure have certain limitations. These reactions are as such: D plus glucose does not form crystalline sodium bisulfite with sodium hydrogen sulfide. D plus glucose does not respond to Schiff's reagent. Although glucose reacts with hydroxylamine, but glucose pentaacetate does not react with hydroxylamine. D plus glucose forms isomeric methyl glucosides. Normally, 2 moles of methanol reacts with 1 mole of free aldehyde to form an acetal, but glucose, which should have one free aldehyde group, when treated with methanol in presence of dry HCl gas, it reacts only 1 mole of methanol to form a mixture of 2 methyl D glucosides, that is methyl alpha D glucosides and methyl beta D glucosides. Reactions are given here. These glucosides do not reduce Tollens reagent, failing solution, and do not undergo mutarotation. Evidences in favor of ring structure. Let us consider evidences in favor of ring structure. Haworth in 1926 suggested that glucose contains a 6-membered ring structure in which 5 carbon atoms and 1 OH group are involved in hemiacetal formation. The 6-membered ring is like pyrene and thus called pyranose form. D plus glucose exists in 2 stereoisomeric forms, that is alpha D glucose and beta D glucose. The properties of these two, property and structure of these two are given below. Evidences in favor of ring structure of glucose. First evidence is phenomenon of mutarotation exhibited by glucose anomers can be easily explained in terms of cyclic structure. That means cyclic structure of glucose can explain mutarotation of glucose. The ring opens up to give open chain form, which then recloses either in the reverted position or in original position, giving an equilibrium mixture of 2 anomers with a small amount of open chain form. It means when alpha D glucose solution is kept for some time, it automatically itself converted into beta D glucose and comes into equilibrium through open chain structure. This is called mutarotation. Since amount of open chain form is very small, reaction of D plus glucose with Schiff's reagent sodium hydrogen sulfide and with ammonia are not effective. In this second point, it is explained that why D plus glucose does not respond with SIPS reagent. Uh, Regarding ring structure of glucose is here. Formation of two anomeric methyl glucosides can be explained in terms of cyclic structure of glucose. When D plus glucose reacts with methanol in presence of dry HCl gas, two anomeric methyl glucosides that are methyl alpha D glucosides and methyl beta D glucoside are formed. They do not undergo mutarotation. It means methyl alpha D glucoside as well as methyl beta D glucoside do not undergo mutarotation because these two structures do not have free aldehyde group. Since they are acetal, acetals do not react with alkalis. They do not react with alkalis. The formation of these anomers prove the cyclic structure of glucose. Fourth evidence in favor of ring structure is formation of two anomeric glucose pentaacetate, also evidence of cyclic structure of glucose. When glucose treated with acetic anhydride or acetyl chloride, a mixture of two anomeric alpha D glucopyranose pentaacetate and beta D glucopyranose pentaacetate are formed. Of these two alpha D glucopyranose pentaacetate and beta D glucopyranose pentaacetate are given here. These pentaacetate do not have free OH group at carbon 1 and hence are not hydrolyzed in aqueous solution to produce the open chain aldehydic form and hence do not react with hydroxylamine to form glucose oxime. The formation of these pentaacetate proves the ring structure of glucose. We are going to establish the ring structure of glucose. In principle, any of hydroxy group in glucose may be at C number 2, C number 3 or C4, C5 or C6 could have been involved in cyclic hemiacetal to form 3, 4, 5, 6 and 7 membered ring structure of glucose. This line explains that let us consider the glucose is cyclic and the cyclic structure may contain 2 carbon, 1 oxygen, 3 carbon, 1 oxygen, 4 carbon, 1 oxygen, 5 carbon, 1 oxygen or 6 carbon, 1 oxygen. Altogether 3, 4, 5, 6 or 7 membered ring. Maybe. Now let us explain one by one. The formation of 3 and 4 membered rings can be ruled out because of their instability. That means 3-membered ring or 4-membered ring are not stable due to high strain. Such type of structures do not such type of structure are not stable. Similarly, a 7-membered ring is also not stable, is also ruled out because this ring requires higher value of entropy of activation. Let us now consider the experiments which have established that the actual size of ring in glucose is 6-membered and not 5-membered. That means glucose is cyclic, and cyclic glucose contains 6 altogether atoms in ring, 5 carbon and 1 oxygen. 6-membered ring is proved by various evidences, and we are considering that evidences through which we will prove that the glucose cyclic structure of glucose contains 6-membered. When D plus glucose is treated with methanol in dry HCl, a mixture of alpha D methyl glucoside and beta D glucoside are formed. From mixture, beta D glucoside, that means the first structure, beta D glucoside, we can see below, is separated. This is treated with dimethyl sulfate in alkaline solution, that means in NaOH solution. As a result, we will get structure number 2, that means methyl 2, 3, 4, 6 tetra O-methyl beta D glucoside. Structure 2, which was present in previous slide, on hydrolysis with dilute HCl gives a structure 3, that means 2, 3, 4, 6 tetraomethyl 1 beta D glucoside, that is a structure number 3, which contains a small amount of open chain structure, that is structure number 4. Here the name of structure number 4 is also given, tetraomethyl 1 beta D glucose in equilibrium. Now let us consider that this fourth structure contains a free OH group and 4 methoxy group and 1 aldehyde group, 1 free aldehyde group. OH group must certainly be present on that carbon which was originally involved in ring formation. That means which was originally in structure number 3 present in ring structure. It may be C5 or C4. Let us decide which one of the carbon was involved or is involved in ring formation, whether it is C5 or C4. To decide this, structure number 3 is oxidized with nitric acid, HNO3. As a result, a mixture of structure 6 and structure 7 are obtained. The fact is this: when structure 3 is oxidized with nitric acid, initially an intermediate keto acid is formed, and this intermediate keto acid then converted into trimethoxyglutaric acid or dimethoxysuccinic acid. These two are formed from intermediate keto acid, which is formed on the oxidation of 2,3,4,6 tetraomethyl 1 beta D glucoside, that is from structure number 3. This is possible, that means the formation of 6 and 7 only if oxidative cleavage of intermediate keto acid, that is structure number 5, occurs on either side of carbon 5 in glucose. Thus, it is this C5OH which is involved in ring formation, and hence actual size of ring in glucose is 6-membered, not 5-membered. Here we are considering if it could be that the glucose has 5-membered rings in which 4 carbon atoms and 1 oxygen atom were involved. In that case, trimethoxyglutaric acid would not have been formed. Instead, only a dimethoxysuccinic acid and methoxymalonic acid would have been obtained. The whole process of different reactions with their resulting structures are given here, which prove that on oxidation with nitric acid, dimethoxysuccinic acid and methoxymalonic acid were formed. That is not in case of glucose we are getting. That's why it is proved that in glucose ring is not 5-membered, ring is 6-membered. Finally, we have come to the conclusion that glucose is ring structure. Glucose has ring structure and ring size in glucose is 6-membered. This has been confirmed by X-ray analysis. On the basis of above discussion, we have come to the conclusion that alpha-D glucose is alpha-D glucopyranose as given by Haworth projection formula here below. Now, two types of structure of alpha-D glucose are given. You are free to write in either way. Both are same. Haworth formula is second one.